can you solve these 6 calculus problems? If you've got A-level exams coming up shortly, these are going to be fantastic practice for those exams. So pause the video, have a go at the questions, and the solutions will follow shortly. We'll get started with problem number 1, which is a differentiation problem. So before we start to try and differentiate this, I want to rewrite it. I'm going to use the fact that if I'm square rooting something, I'm taking it to the power of a half, and because it's 1 over that, I can use a negative power to rewrite this. So this will become 4x squared minus 5 to the power of negative a half. The next thing I'm going to do is to differentiate this, I'm going to use the chain rule because I've got a function within a function. So I'm going to let the bit inside the bracket equal u, where that u is just 4x squared minus 5. I find dy by du. So multiply by the power, take 1 off the power. And then I differentiate du by dx. Then what I'm going to do, multiply dy by du by dx. Because this is giving me what I want, the dy by dx. So I multiply these two things together. Minus a half times 8 is minus 4. Then I've got the x and the u to the power of minus 3 over 2. But I want to leave my answer in terms of x. I don't want any u's in there. So what I'm going to do is put that u equals 4x squared minus 5 back in. And there we go, that is our first one done. If you don't necessarily have to use the chain rule in this kind of formal way here. With practice, you probably will just see that what you do when you've got these sorts of problems is you'll multiply by the power, multiply by the derivative of what's in your bracket, and then take the power of your bracket down by 1. So as you do more practice, you'll probably start using that. But just in these stages, it's good to show where it all comes from. Right, we'll have a look at problem number 2 now. So I had a few people ask me about some problems with rates. So I thought I'd go through one of these rates problems here. So we've got a cylinder that has a height that's 3 times its radius. We're also told the radius is increasing at a rate of 0.5 centimeters per second. What I'm going to do here is I'm going to extract that information that I've got the radius increasing at a rate of 0.5 centimeters per second. Well, this would just be dr by dt, okay? Because it's the rate of change of the radius. So that would be dr by dt as a derivative. The units can also give you a little hint as to how that derivative should be set up. So note that dr by dt is 0.5. And I'm going to find the rate at which the volume of the cylinder is increasing at the instant when the radius is 5 centimeters. So what the question is asking me to do is it's asking me to find dv by dt. Okay, if you want the rate at which the volume is increasing, the question is saying find dv by dt when r is 5. So it's kind of good just to unpick what you know here, what this question's telling you, and also try and actually figure out what is it actually asking you to do. Okay, it asks you, wants you to find dv by dt when r is 5. So we don't actually have dv by dt here. We've got dr by dt, but we haven't really made much use of that first bullet point. Okay, we're told that a cylinder has a height that's 3 times its radius. Well, I can think about equations that relate volume and radius together, in that I know that the volume of a cylinder would be pi r squared times the height. But I've got two variables here. I've got r and h. So let's make use of that other fact that the height of the cylinder is 3 times its radius. So the height is just 3r. Now what this enables me to do is substitute in h equals 3r. So now what I can do is write the volume all in terms of r. Because then what I can do is I can find dV by dr with this. So dV by dr, if we differentiate this, remember pi is just a constant, so still, no special rules for that. Still multiply by the power and take 1 away from the power. So you've got there dV by dr. So why is that useful? Well, we want to find dV by dt. Okay, this is what we're trying to find. And I can make use of the fact that I know what dV by dr is, and I also know what dr by dt is. And if we multiply them together, then those dr's will cancel and you'll get your dV by dt. So let's multiply our dV by dr by the dr by dt, the 0.5 that we found at the start. So I know that dV by dt is going to be, if I simplify this, 4.5 pi r squared, but that's what it is in general. What we want to look at is what is the rate, so at the instant when the radius is 5, what is that rate going to be? So when r equals 5, we just sub in r equals 5 into that 4.5 pi r squared. When we do that, we get 112.5 pi. And if you wanted some units, it's the volume with respect to time. So this would be centimetres cubed, because our radius was in centimetres, and this would be per second. So your units would be centimetres cubed per second. So the goal with those types of questions is try and figure out what you are trying to find, look at what you already know, and then look at if you can come up with some other derivatives from information that you either have, or things like you can just go back and think like we did here, volume of a cylinder, and try and come up with another derivative to help you find the one that you actually are trying to find. The final problem on the differentiation side, we'll look at next question 3. So we've got that x is cosec squared y, and we're going to find dy by dx. Now, what I'm going to do here, rather than rearrange this to make y the subject, is I'm going to just find dx by dy, because that's going to be far simpler than just rearranging it to make y the subject and then do dy by dx. I can find dx by dy with not too much difficulty, and then I can do the reciprocal of that to get me dy by dx. So let's go ahead and do that. Yeah, again, let's use the chain rule. I'm going to let u be cosec y. So that makes xu squared, where that u is cosec y. And then as I do, I find dx by du and du by dy. Now, differentiating cosec y, that's a result that is in your formula book. So just make sure that you've got your formula book handy when you're doing your these differentiation and integration problems. So when you differentiate cosec y, you're going to get minus cosec y cot y. Okay, and as I said, we're not finding dy by dx right away. We're going to find dx by dy first. So we get that by timesing the dx by du and the du by dy together. And then I'm just going to substitute the u, which is cosec y. So I get this result here. But this isn't dy by dx. This is dx by dy. So dy by dx will just be the reciprocal of this. So it will just be 1 over all of this. Now, there's no this question didn't have any requirement of how to leave it, but I could actually go a little bit further than this. I could write this in a slightly nicer form. And firstly, I've got 1 over minus 2, so I can write this as minus a half. But if I'm doing 1 over cosec squared, well, remember, 1 over cosec is just sine, because 1 over sine is cosec. So 1 over cosec squared would just be sine squared. And 1 over cot is just the same as tan. So I could leave it as this slightly nicer form here at the end. Okay, hopefully we're getting on okay. 3 questions down, 3 more to go. So we're at the halfway point here. So on to question number 4 now. First of our integration problems. So this is the first one I think I've shown where there's some limits. So this is a definite integral now. So we're going to need to integrate this, and then we're going to need to substitute in these limits that we're given. Okay, in this question, we're going to leave our answer in terms of a. So the first thing we're going to do is we're going to integrate e to the power of 2x. So if I do this, put my result in these square brackets. If I integrate e to the 2x, I look at that coefficient of x, and if I was differentiating, I'd be multiplying by it, but I'm integrating, so I'm going to be dividing by it or timesing by the reciprocal of it. So I'm going to be timesing this e to the 2x by 1 over 2, or dividing it by 2. So I've integrated e to the 2x, and now I'm going to substitute in my limits of natural log of 3a and natural log of a. So firstly, we put in our upper limit. So where I replace the x with natural log of 3a. And then I'm going to substitute in the lower limit of natural log of a. So remember, when we put in we take this away here. We put in that lower limit. Okay, so we subbed in those 2 limits there. And then what I'm going to do is I'm going to, because this isn't just e to the natural log or something, I'm just going to use the third law of logarithms, the power law, whatever you want to call it, whatever you prefer to call it, to bring this 2 up as the power. So I'm going to bring the 2 up as the power, which means I need to square my 3a. Okay, so the 3a is going to get squared to make that 9a squared. Okay, just using this law here. Okay, just one to remember from your laws of logs. And then what I'm going to do is this one here, I'm also going to use that power law. I'm going to bring that 2 up to be the power. So you're just going to be squaring the a to get a squared. But then I'm going to use another rule that I can use with logarithms, and that's that when we have e to the natural log of x, that just becomes x. So where you have e to the natural log of 9a squared, it just becomes the 9a squared. Don't forget times by this half, but you just got e to the natural log of whatever is here. It's just going to be what you have, so the 9a squared. And I do the same for the other term as well. So e to the natural log of a squared will just be a squared. And then you just take these away. So a half of 9a squared minus a half a squared will just be 4a squared. So a lot of that, to be fair, wasn't much test of integration. It was more a test of laws of logarithms. But a lot of integration problems that you will find do actually rely on use of logarithms towards the end to simplify answers. Or sometimes it might be questions like this where it isn't, you haven't got, it's in terms of a or k or something like that. Right, 2 more to go then. We're going to look at question 5. So there'll be a couple of ways that you can do this, but if you want a little hint, if you kind of weren't sure how to get started with it, but maybe want to have another go, a hint would be use a substitution here. I'm going to do this one by a substitution. So I'm going to let that bit inside the square root be u. So I'm going to say let u be 5 plus 2x. So if you want to have another go at this with this substitution, feel free to pause here and then check if you got the answer. But I'll show you how it works when we use this substitution. So generally when we make a substitution, what we want to do is then differentiate that. In this case, that would be finding du by dx, which gives us 2. Because it's usually going to be useful to have this derivative, because what we want to achieve when we are integrating by substitution is we've got all x's at the moment, but we need to get everything in terms of u. And also we need to make sure we've got a du, because I can't integrate with respect to u if I don't have a du there. So by differentiating, we're going to be able to replace our dx with something in terms of du. So if u is 5 plus 2x, du by dx would just be 2. And dx would just be a half du. So that's going to come in handy when we start to sub everything in shortly. So I can replace the dx with a half du. The 5 plus 2x gets replaced with a u. Everything is nearly in terms of u, with the exception of that x. So I'm going to need to replace that x with a u as well. So that x, well, using that substitution, I could rearrange u equals 5 plus 2x to get u minus 5 over 2. So now what I can do, I'll be able to replace the x with something in terms of u. The 5 plus 2x gets replaced with a u, and the dx will get replaced with a half du. Everything's going to be in terms of u, and I've got a du as well. That's the goal here. So, as I said, the x, we replace it with u minus 5 over 2. The 5 plus 2x gets replaced with u. And then the dx, well, I'm replacing that with a half du. Okay, I've got a lot of brackets here, but I'm trying to just show you where each of these things have been, how they've been substituted in. So let's make this a little bit tidier. What I'm going to do now is I'm going to take out my constant. Okay, you can take out constants on the outside of this integral, but you can't take out u's. So I've got a half in the first bracket. I've got another half in the third bracket. So half times a half is a quarter. I'm just going to move that on the outside of this integral here. And then I'm going to do u times u to the power of a half. And then we'll do minus 5 times that u to the power of a half. And I'm integrating that with respect to u. Right, so what I can do is I can integrate something that's hopefully a lot simpler now. So this u to the power of 3 over 2, add 1 to the power and divide by the new power. So dividing by 5 over the 2 is the same as multiplying by 2 over 5. And then u to the power of a half becomes u to the power of 3 over 2. Divide by a new power, 5 divided by 3 over 2. That's the same as multiplying by 2 over 3. Don't forget that all of this gets multiplied by a quarter. Just make sure we've got our plus c in there as well. And then finally, we just need to remember that we don't want to leave it in terms of u. So let's sub in our u back in. So sub in that 5 plus 2x back in. And I'm also going to multiply by the quarter here as well. So a quarter times 2/5, 1 over 10. And replace the u with 5 plus 2x. Times the quarter and the 10 over 3 together. And yet again, put the u plus u equals 5 plus 2x back in there as well. Okay, we're nearly there then. One more to go. And I thought we'd finish on some differential equations. So we're going to find the general solution to this problem here. So the first thing I'm going to think to do is that I need to have one side have the dy on and the other side is going to have the dx. Because one side I'm going to integrate with respect to y, the other side I'm going to integrate with respect to x. So I'm going to start by timesing both sides by dx. But there's a problem here, and that's that the side with the dy on, I've got a function of x, and the side that has the dx on has a function of y. So what I want to do is I want to get the side with the dy having a function of y on, and I want to get my function of x on the side with the dx. So what we're going to have to do is divide both sides by 5y, and then divide both sides by cos squared. Now I've got all my y's on the same side as the dy, I've got all my x's on the same side as the dx. The next thing I'm going to do is add the integral symbols to both sides. Okay, so basically I'm just integrating both sides here. But before I actually do the integration, because I can see on the right hand side that's going to be quite tricky to integrate in its current form, I'm just going to rewrite what I've got on my right hand side. Because 1 over cos squared is the same as sec squared, which is a result that I have in my formula book for how to integrate that. But I wouldn't just have 1 over cos squared in the formula book there. So thinking of it as sec squared instead of 1 over cos squared is going to make it a lot easier to do my integrating. Okay. On the other side, don't necessarily have to do this, but you might just find it helpful to take the fifth on the outside of the integral, just take that constant out, and then just have the 1 over y there. Right then, so now let's actually integrate both sides here. Okay, so wherever you see that integral symbol, that is the instruction that you will need to integrate. So we're going to integrate the left-hand side. And when you integrate 1 over y, you just get natural log of y. And then we mentioned it earlier that the integral of sec squared is one that's in your formula book. And the result of that, when you integrate sec squared, you get tan x. Okay, you might recall that when you differentiate tan, you get sec squared. Finally, I'm going to put my constant of integration here, my plus c, on the right-hand side. It doesn't matter which side it goes on, as long as you have a plus c on one side here. Okay, so yeah, again, this question hasn't actually told me to go any further here, but I am going to start to simplify this, and I'm going to write this as y as a function of x, because often we might be asked to do that. So to do that, I'm going to start by multiplying both sides by 5. Note that I don't have to make this a 5c because this is just a constant that I don't know what it is at this point. So there's no point in writing it as 5c because that still is just a constant within itself. So I'm just going to leave it still there as c. But do make sure though that the tan gets multiplied by 5. Okay, so we have natural log of y equals 5 tan x plus c. What I can then do is to get y on its own, I'm going to need to do e to the power of this right hand side. Okay, remember natural log is log to base e. So if you're switching it from that log form into exponential form, you'd get y equals e to the power of 5 tan x plus c. But I can go even better than that because using my laws of indices, I can rewrite e to the power of 5 tan x plus c as e to the power of 5 tan x multiplied by e to the power of c. And e to the power of c is just a constant. Okay, you're doing e to the power of some number. So that in itself is a constant. So I'm just going to rename this a, and then I have my general solution. Okay, you might then have a question that gives you some boundary conditions in which you can then find what that missing constant is and actually get a particular solution, but we're just going to leave it there. So hopefully you got an okay. Let me know if there's anything there that you struggled with, would like more insight on, or any particular types of problems that you would like to see in the future.